Alright everybody, my name's David. I'm heading home. I'm listening to Electrical Engineering. It's a book about electrical engineering, okay? Basics of electrics, okay?
A varying coil is connected to the power source, and the secondary coil is connected to the load. When an AC voltage is applied to the primary coil, it creates a varying magnetic field in the core. This varying magnetic field induces an electromotive force, or EMF, in the secondary coil, resulting in an output voltage that is proportional to the turns ratio of the coils. Key features and uses of transformers include voltage step up or step down, depending on the turns ratio of the coils. They are crucial for adjusting voltage levels in power transmission and distribution networks, ensuring efficient delivery of electricity over long distances while minimizing energy losses. Transformers also isolate electrical circuits, providing protection from power surges and electrical faults. In addition to their role in power systems, transformers are used in various applications, such as in electronic devices, audio equipment, and telecommunications. They contribute significantly to the reliability and efficiency of electrical infrastructure, allowing for the safe and effective utilization of AC power in diverse industrial, commercial, and residential settings. Diodes and transistors. Diodes and transistors are fundamental semiconductor devices that play critical roles in modern electronics. Diodes are semiconductor devices that allow current to flow in only one direction. They consist of two layers of semiconductor material, N-type, negative, and P-type, positive, joined together.
Yo, what's good?
When a positive voltage is applied to the P-type material relative to the N-type material, forward bias, the diode conducts current easily. In reverse bias, negative voltage applied to the P-type material, the diode blocks current flow, acting as a one-way valve for electricity. Diodes are used in rectification to convert AC to DC, in signal demodulation and detection, and in voltage regulation. Transistors are semiconductor devices used to amplify or switch electronic signals and electrical power. They consist of three layers of semiconductor material, NPN or PNP, forming two junctions, emitter-based and collector-based. In a common NPN transistor, when a small current flows between the base and emitter, base current, it controls a larger current flow between the collector and emitter, collector current. This amplification capability allows transistors to function as electronic switches and as amplifiers in circuits. Transistors are essential components in digital logic circuits, amplifiers, oscillators, and in controlling motors and lights in automation and control systems.
I'm glad you're here too.
Both diodes and transistors are integral to the operation and design of electronic circuits, enabling the creation of sophisticated devices and systems that power modern technology across various industries, from telecommunications and computing to automotive and aerospace applications. Understanding their principles and applications is crucial for engineers designing and optimizing electronic systems for efficiency, performance, and reliability. 6. Power generation and distribution. Power generation and distribution form the backbone of electrical infrastructure, ensuring electricity is produced efficiently and delivered reliably to consumers. Power plants. Power plants are facilities designed to generate electrical power on a large scale. They convert various energy sources into electricity using turbines connected to generators. The main types of power plants include 1. Fossil fuel power plants. These plants burn coal, natural gas, or oil to produce heat. This heat is used to generate steam, which drives turbines connected to generators. Fossil fuel power plants are widely used due to their ability to provide continuous and reliable power. 2. Nuclear power plants. Nuclear reactors use nuclear fission to generate heat.
Yes, so Emma, I'm listening to a book about electricity. So yes, I'm not the one speaking right now.
Heat is used to produce steam, which drives turbines connected to generators. Nuclear power plants produce large amounts of electricity without emitting greenhouse gases, but require careful management of radioactive waste. 3. Hydroelectric power plants. These plants use the energy of flowing water to generate electricity. Water is collected in reservoirs behind dams and released spin generators to produce electricity. Hydroelectric power plants are renewable and provide reliable. 4. Wind power plants. Wind turbines convert the kinetic energy of wind into mechanical energy, which drives generators to produce electricity. Wind power plants are renewable and increasingly used for their environmental benefits. 5. Solar power plants. Solar photovoltaic, or PV, and solar thermal power plants convert sunlight into electricity. PV plants use solar panels to directly convert sunlight into electrical energy, while solar thermal plants use mirrors or lenses to concentrate sunlight onto a small area, generating heat to drive turbines connected to generators. Each type of power plant has unique advantages and considerations regarding cost, environmental impact, reliability, and scalability. Power plants are critical components serving consumers worldwide. Transmission lines. Transmission lines are essential components of electrical power systems, responsible for transporting electricity over long distances from power plants to distribution networks and ultimately to consumers. These high voltage lines are designed to efficiently transmit large amounts of electrical power, minimizing energy losses over extended distances. Key features of transmission lines include high voltage. Transmission lines operate at high voltages, typically ranging from 69 kV to 765 kV or higher. Higher voltages reduce the amount of current needed to transmit a given amount of power, thereby minimizing resistive losses in the lines. Power losses. While transmission lines are designed to minimize energy losses through efficient conductors and insulation, some amount of power is inevitably lost as heat due to resistance in the conductors. Insulation and support structures. Transmission lines are supported by tall towers or poles and are insulated to prevent electrical leakage and ensure safe operation, even in adverse weather conditions. Regulation and control. Voltage regulation and reactive power control are critical for maintaining the stability and reliability of transmission networks. Transformers and reactive power compensation devices are used to manage voltage levels and improve power quality. Transmission lines play a crucial role in delivering electricity generated from various sources, including fossil fuels, nuclear, hydroelectric, wind, and solar power plants to meet the energy demands of residential, commercial, and industrial consumers. They form a vital link in the interconnected grid system that enables efficient and reliable power distribution across regions and countries. Distribution networks. Distribution networks are crucial components of electrical power systems responsible for delivering electricity from high voltage transmission lines to homes, businesses, and industries. Unlike transmission lines that transport electricity over long distances at high voltages, distribution networks operate at lower voltages, suitable for safe and efficient local consumption. Key aspects of distribution networks include voltage levels. Distribution networks typically operate at lower voltages than transmission lines, ranging from 110 kV down to 400 V for residential and commercial consumers. This voltage reduction occurs through step-down transformers located at substations near residential and commercial areas. Substations. These facilities play a pivotal role in distribution networks by stepping down high voltage electricity received from transmission lines to lower voltages suitable for local distribution.
It's so cool to see.
Substations also house equipment for voltage regulation, switching, and protection. Distribution lines. Once voltage is reduced at substations, electricity is carried through distribution lines consisting of overhead lines or underground cables. These lines deliver electricity to transformers mounted on utility poles or pad-mounted transformers near buildings. Load management. Distribution networks manage varying electrical demands across different times of the day and seasons, ensuring reliable supply to consumers. Utilities employ load management techniques such as peak shaving and demand response programs to balance supply and demand effectively. Reliability and maintenance. Ensuring the reliability of distribution networks requires regular maintenance of equipment and infrastructure, including inspections, repairs, and upgrades. Fault detection and rapid response mechanisms are critical for minimizing downtime and ensuring continuous power supply. Distribution networks from the last stage in the delivery of electricity to end users, providing essential services for lighting, heating, cooling, and powering electrical appliances in homes and businesses. Their efficient operation is vital for supporting economic activities and enhancing quality of life in urban, suburban, and rural areas alike. 7. Electric machines. Electric machines refer to devices that convert electrical energy into mechanical energy or vice versa. They play crucial roles in various industrial, commercial, and residential applications, contributing to the efficient operation of modern technology. Here's an overview of electric machines. Motors and generators. Motors and generators are essential electromechanical devices used in various applications to convert electrical energy into mechanical energy and vice versa. Electric motors. Electric motors operate by utilizing the interaction between magnetic fields and electric currents. When electrical current passes through the motor's windings, it creates a magnetic field that interacts with the magnetic field produced by the motor's permanent magnets or other windings. This interaction generates a force that causes the motor's rotor to rotate, converting electrical energy into mechanical energy. Electric motors are widely used in industrial machinery, household appliances, transportation, such as electric vehicles and trains, and various mechanical systems. Generators. Generators, also known as alternators, work on the principle of electromagnetic induction to convert mechanical energy into electrical energy. When a generator's rotor is mechanically driven to rotate within a magnetic field, it induces an electric current in the generator's windings. This current is then transferred through electrical conductors to external circuits, where it can be used to power electrical devices or be transmitted over long distances through power lines. Generators are essential components in power plants where they convert mechanical energy from turbines driven by steam, water, wind, or other sources into energy for distribution grids. Both motors and generators are critical in enabling the efficient conversion and utilization of electrical and mechanical energy in modern industrial, commercial, and residential systems. Understanding their principles and applications is essential for engineers designing, operating, and maintaining systems that rely on these electromechanical devices. Transformers. Transformers are essential devices in electrical engineering, used primarily to transfer electrical energy between circuits through electromagnetic induction. They consist of 2 or more coils of insulated wire wound around a core made of ferromagnetic material, such as iron or steel. The primary coil, connected to a voltage source, induces a varying magnetic field in the core when an alternating current, or AC, flows through it. This varying magnetic field, in turn, induces a voltage in the secondary coil connected to the load circuit. The number of turns in the coils determines the voltage ratio between the primary and secondary sides of the transformer. Transformers serve several critical functions in electrical systems. Voltage transformation. They step up or step down the voltage levels between different stages of power transmission and distribution. High voltage transmission reduces power losses over long distances, while lower voltages are safer and more practical for use in homes and businesses. Isolation. Transformers electrically isolate the primary and secondary circuits, providing protection against electric shock and preventing ground loops in sensitive equipment. Impedance matching. They match the impedance of the load to the source, optimizing power transfer efficiency. Power distribution. Transformers play a central role in distributing electrical power from generating stations to consumers via transmission and distribution networks. In addition to these primary functions, transformers are crucial in various applications, including industrial machinery, consumer electronics, and telecommunications equipment. They come in different types and sizes, tailored to specific voltage and power requirements. Understanding the principles and applications of transformers is essential for designing efficient and reliable electrical systems that meet the diverse needs of modern society. Control systems. Control systems are integral to engineering disciplines, ensuring automated regulation and management of processes or devices. They monitor inputs and outputs, adjusting operations to achieve desired outcomes or maintain stability. These systems are pervasive across industries such as manufacturing, aerospace, automotive, and telecommunications. Central to control systems is feedback, where information about a system's output is fed back to adjust its input or parameters. This feedback loop enables systems to self-regulate and correct deviations from desired conditions. Control systems can be classified into several types, including 1. Open-loop control systems. These systems operate without feedback. They set parameters based on known relationships and assume ideal conditions, lacking the ability to correct errors or respond to disturbances. 2. Closed-loop or feedback control systems. These systems adjust operations based on feedback from outputs, ensuring greater accuracy and stability. They use sensors to measure output variables, compare them to desired values, set points, and adjust inputs accordingly. 3. Digital control systems. These systems use digital computing techniques for processing feedback and generating control signals. They offer precision, flexibility,
Yes, I do.
and the ability to implement complex algorithms for advanced control applications.
I do appreciate
Control
you still being
systems
here.
employ various components,
Thanks for riding with me.
including controllers, actuators, sensors, and communication interfaces. Controllers compute necessary adjustments based on feedback signals, while actuators execute control commands by manipulating physical variables. Sensors detect changes in system variables, providing feedback to controllers for real-time adjustments. Applications of control systems range from simple thermostat control in HVAC systems to sophisticated automated processes in industrial manufacturing and robotic systems. Advances in control theory, computational capabilities, and sensor technology continue to drive innovations in automation, efficiency, and reliability across diverse industries. 8. Electronics and signal processing. Electronics and signal processing are foundational disciplines in modern technology, playing crucial roles in communication, computing, and control systems. Analog and digital electronics. Analog and digital electronics are fundamental branches of electrical engineering, each playing distinct roles in signal processing, communication, and information technology. Analog electronics. Analog electronics deals with continuous signals that vary over time and can take any value within a range. These signals are represented as voltages or currents that correspond directly to the information being processed. Analog circuits manipulate these signals using components such as resistors, capacitors, inductors, and operational amplifiers, or op-amps. Applications of analog electronics include audio amplifiers, radio receivers, analog sensors, and analog to digital converters, or ADCs, used in signal processing. Digital electronics. Digital electronics, in contrast, operates with discrete signals that exist in one of two states: high, or logic 1, or low, logic 0. These signals are processed using digital circuits that perform logical operations, arithmetic calculations, and data storage. Key components include logic gates and, or, not, etc., flip-flops, registers, and microprocessors. Digital electronics forms the foundation of modern computing, telecommunications, and information systems, enabling the creation of digital devices such as computers, smartphones, digital cameras, and digital audio players. Both analog and digital electronics complement each other in various applications. Analog electronics excel in processing real-world signals with high fidelity and precision, while digital electronics offer advantages in reliability, flexibility, and ease of processing and storage of large amounts of data. Understanding the principles and applications of analog and digital electronics is essential for engineers designing and implementing systems across diverse industries, ensuring efficient and reliable operation of electronic devices and systems.
So Emma, I just wanted to let you know that I do lose service here, so my video will probably end soon. I do just want to thank you again for hanging out with me. You've hung out with me most of the day today, so I just want to say thank you, and I really hope to see you again. And again, I'm grateful for you sharing and getting to know you a little bit today. So I will continue with this until it stops. So again, everyone, if my video stops, I just want to thank you so much for being here. My name is David Hayes. Thank you.
Across diverse industries, ensuring efficient and reliable operation of electronic devices and systems. Signal processing basics. Signal processing is a foundational discipline in electrical engineering and computer science that revolves around analyzing, modifying, and interpreting signals. Signals represent variations in physical quantities over time or space and can be categorized into analog signals, which are continuous, and digital signals, which are discrete and quantized. In signal processing, signals undergo various transformations such as filtering, modulation, demodulation, compression, and enhancement.
I'm in a storm, ain't I?
These operations are aimed at extracting meaningful information, reducing noise, or preparing signals for transmission or storage. Mathematical techniques such as Fourier transforms or Fourier, Laplace transforms, convolution, and correlation are employed to analyze signal characteristics, frequency components, and time domain behaviors. The application of signal processing are widespread and diverse. They include telecommunications, audio and speech processing, image and video processing, radar and sonar systems, biomedical signal analysis, and control systems. Digital signal processing, or DSP, refers to the implementation of these techniques using digital systems like computers and DSP chips, offering advantages in accuracy, flexibility, and reproducibility. Signal processing continues to evolve alongside advancements in computing, algorithms, and sensor technologies, driving innovation across industries and enhancing the efficiency and reliability of modern technologies and systems. Communication systems. Communication systems are essential frameworks that facilitate the efficient exchange of information across various platforms and mediums. They enable the transmission, reception, and processing of signals to ensure reliable data conveyance. These systems encompass a broad spectrum of technologies and applications. They include telecommunication networks like telephone and cellular systems, as well as the internet, which transmit voice, data, and multimedia over long distances. Broadcasting systems, such as radio and television, deliver audiovisual content to large audiences, while wireless communication employs radio waves, microwaves, or infrared signals for mobile communications, Wi-Fi networks, and satellite links. Data communication facilitates data exchange among computers and digital devices via local area networks, or LANs, and wide area networks,
Bye-bye,
or
everybody.
WANs.